Welcome to Physics 2201. I'm Jim Simmons, the instructor for the course, and in these video lectures I use the microphone here since the computer doesn't necessarily pick up sound very well. So everything we do, and I do mean everything, literally everything we do in Physics 2201 is based on our ideas about motion. So we start by thinking about motion. And the idea is that you ought to be able to describe motion in a bunch of different ways. Algebraically, or a verbal description, or describe it with graphs or with other kinds of diagrams. So we start with a very simple representation, a very simple kind of diagram called a motion diagram. And in the motion diagram, we're just imagining the moving object to be reduced to one point-like lump of mass. And at various times, you just look to see where that lump of mass is. So, there are three basic types of motion diagram, and any complicated kind of motion will be described by some combination of those basic three types. So you've got one type of motion diagram that illustrates constant speed, always moving the same distance in the same length of time. So here's how it works. You're watching something that's moving, and at some point you just start the stopwatch. That's the moment when you actually start watching the object. And so at that time when you start watching, here's the location. Just put a dot there to represent that as the location at time 0, the moment you started the stopwatch. Then you wait a little while, 1 second, half a second, 1 minute, 30 seconds, any kind of time interval. And at the end of that time interval, you look again to find the location of the object. And at that location, you put the next dot. And we label that 1 because that's the location of the object at the end of the first time interval. The end of the first 1 second time interval, or half second time interval, or at the end of the first 1 minute time interval, or at the end of the first 30-second time interval, whatever. And then you repeat the process. You always wait the same length of time. Every time interval from one location measurement to the next is always the same length of time. So you wait the same, so you note where the object is at this time, then you wait the same length of time, and you note that the object is there. That's the location of the object at the end of the second time interval. The time would just be 2 time intervals after the start. And likewise, at the end of the third time interval, the object is here. At the end of the fourth time interval, the object is here. And note that the spacing between consecutive dots is the same, indicating that during the first time interval, the thing traveled this far, and during the second time interval, which is the same amount of time, it traveled the same distance. And then in the third time interval, which is the same amount of time, it traveled the same distance. Well, always traveling the same distance in the same amount of time is just another way of saying constant speed. It's not speeding up, not slowing down. So, constant speed, represented by a motion diagram where the dots representing locations are evenly spaced. And then you might guess that a second basic type of motion diagram would correspond to speeding up. And that would look something like this. When you first start watching the object, there it is. That's where you turn on the stopwatch. That's where it is at time 0. That's where it is before any time intervals have elapsed. And then at the end of one time interval, there it is. At the end of the second time interval, there it is, and so forth. But notice that during the second time interval, it traveled farther than it did during the first time interval. And then at the end of the third time interval, it's here. So during the third time interval, it traveled from here to here, and that distance is farther than the distance traveled during the second time interval. Here's the distance traveled during the first time interval. Here's a bigger distance traveled during the second time interval. Here's an even bigger distance traveled during the third time interval. Here's an even bigger distance traveled during the fourth time interval. And here's an even bigger distance traveled during the fifth time interval. So as time goes by, the object is traveling a greater distance in the same amount of time. Going farther in the same amount of time is just another way of saying that the object is speeding up. And then the third basic type of motion diagram, besides the constant speed diagram and the speeding up diagram, where the spacing increases as time goes by, would be the diagram indicating slowing down. And you might expect that would look sort of the opposite of the speeding up diagram. It would look something like this. Slowing down. Here's where the object is right when you start watching, right when you turn on the stopwatch. There's where the object is before any time intervals have elapsed, or that's where it is when 0 time intervals have elapsed. And then by the end of the first time interval, it's gone quite a distance. It's initially moving pretty fast. And then during the second time interval, it's going slower than it was during the first time interval. So in that same amount of time, it won't travel as far as it did in the first time interval. So by the end of the second time interval, it's traveled only this far, as opposed to twice as far during the first time interval. Then in the third time interval, it's going slower still. So by the end of the third time interval, it's traveled only that far, less than it did during the second time interval when it went from here to here. And then during the fourth interval, going even slower than before, so it travels an even shorter distance than before. So at the end of the fourth time interval, it's there. It traveled only this far during the fourth time interval, which is shorter distance than it traveled during the third time interval, which is a shorter distance than it traveled during the second time interval, which is a shorter distance than it traveled during the first time interval. As time goes by, the spacing between dots decreases, and that's how you indicate an object is slowing down. Now, I've labeled all the dots with numbers. That's necessary. That's absolutely necessary. Why? Well, let's see here. Let's say I had a graph with dots like this, but didn't have numbers. So without numbers, you don't know the direction of motion. Right here, you know the direction of motion because here's the 0 dot. That is location at the earliest time. And then here's where it is 1 time interval later. And then here's where it is 4 time intervals after the start. So this is the latest location. This is the earliest location. So because you have the numbers here, you know that the motion was left to right. And you know that at later times, it moved a shorter distance. At earlier times, it moved a greater distance per time interval, so that's how you know it's slowing down. Whereas here, you don't know whether this graph represents speeding up or slowing down. If the graph were labeled like this, if the diagram were labeled like that, then of course you'd know that it was slowing down, because during the later time intervals, like the fourth time interval, it travels a shorter distance than it did at earlier time intervals. It's only because of the numbering that you know which time intervals were earlier and which time intervals were later. But we didn't know the numbering here, so the numbering here could have been like that, meaning the motion would have been from right to left. This is the location at the earliest time. This would have been the location at the latest time. So that means if the numbering were like that, then during the earlier time intervals, the object travels a shorter distance, and during the later time intervals, the object travels a greater distance. If the numbering had been like this, that would indicate motion right to left and speeding up. If the numbering had been like this, that would represent motion right to left, or excuse me, left to right, and slowing down. If you didn't have those numbers, if all you had were the dots, you wouldn't know which kind of motion this set of dots represented. You wouldn't know whether it was an object moving left to right and slowing down, or an object moving right to left and speeding up. You need the numbers. There, you must include the numbers for a legitimate, complete, useful motion diagram. Well, let's look at one particular example here. By the end of all this, one thing you should be able to do is, given some kind of description of motion, either a verbal description or a graph, can you draw a motion diagram that represents that same kind of motion? So imagine this. Imagine that you're driving down the street, you see the light turn yellow, but you think you can make it through the intersection before the light turns red. So instead of slowing down for a yellow light, you speed up. But then the light does turn red before you get to the intersection, so you have to slow down very, very quickly. And then part 3, you just stay there, stopped for a little while before the light turns green. So we want a motion diagram that represents all 3 of those different types of motion: speeding up, then moving in the same direction but slowing down, and then not moving at all. So speeding up would be represented by a motion where the motion diagram has increasing spacing as time goes by. So here's where I am right when we start watching and start thinking about the motion. And then at the end of one time interval, there I am. Now I'm speeding up, so I traveled a greater distance per time interval than I did before, so a bigger spacing. And then I'm still speeding up. And then I'm still speeding up, so I travel a greater and greater distance per time interval. But at this point, I see the light turn red, so I have to slow down. And so now slowing down means as time goes by, the spacing between dots decreases. So at the end of the next time interval, there I am. And at the end of the sixth time interval, there I am. And at this location, I have come to a stop. My velocity is 0. And I stay stopped for a while. That means I've arrived at this point at the end of the sixth time interval, but at the end of the seventh time interval, I'm still there. And at the end of the eighth time interval, I'm still there, same location. And at the end of the 9th, 10th, 11th, 12th time interval, I'm still there. And I don't start to move again until after the 16th time interval. So I represent the fact that I'm staying at the same location for a long stretch of for some stretch of time by labeling the dot like this. That means I'm at this location here from the end of the sixth time interval. I arrived at this point at the end of the sixth time interval and I stay at that same location until the end of the 16th time interval. And at that point, I start to move again. So that by the end of the 17th time interval, I'm at a different location. So during the first 4 time intervals, speeding up. And then during the next 2 time intervals, I slow down. I slow down quickly, that is, slowing down a lot quicker than I sped up. And then for the next 10 time intervals, however long that time interval is, for the next 10 of them, I stay put at the same location. So you label the same dot, in other words, the same number, with a whole bunch of different, or the same dot, the same location. You label it with a whole bunch of different numbers, a whole range of numbers. Okay, that's how motion diagrams work. That's just the first step in thinking about motion. It's a simple picture to indicate where you are at different points in time. We want to be quantitative, however, and to do that we need to be able to assign numbers to different locations, and for that we invent coordinate systems. Coordinate systems aren't something that exists out there in nature. They're entirely a construct. They're something that we make up in order to just make it easier to think about motion, make it easier to think quantitatively about motion. And at least for the first couple chapters, for the first couple of weeks, we'll be taking it easy, thinking about just a relatively simple kind of motion, one-dimensional motion, that is just moving back and forth along one line. And of course, when you move back and forth along one line, you can assign numbers to different locations on that line. Just imagine superimposing a number line on top of that line where the motion is taking place. There's your coordinate system. One important element of a coordinate system is the origin, the point that you will call zero location, the zero location. You can choose that at any point that's convenient for you. Let's look at a particular kind of motion when there's just back and forth motion along one line. So here's a number line representing different locations, and here's the origin of our coordinate system, the point that we will call 0, and we'll mark the different locations in meters. x is the variable that we will use for location, and x will always be a certain number of meters. So there's the 1, 2, 3 meter locations, and then here's the -1, -2, -3 meter locations. And let's say that there's some motion that starts here. This is the initial location. So subscript I to indicate that this is the initial location, and it's what? It's a location of -2 meters. Both the absolute value of this and the sign of this are significant, meaningful. The 2 meters means what? It means that if you're sitting at the origin, you have to travel 2 meters to get to this point. And the minus sign means that if you're sitting at the origin, you have to go in the negative direction to get to this point. So 2 pieces of information, a direction indicated by the sign, and a size indicated by the length but through which you have to move. Those two, anything that has those 2 elements, a size and a direction, we call a vector. And it's important to recognize that locations are examples of vectors, something with both a size and a direction. In this case, the size means how far away you are from the origin of your coordinate system. And the direction is indicated by the sign, which tells you which way you have to go if you're starting at the origin and want to get to that point. Well, anything that has a direction, of course, can be represented by an arrow. An arrow will point in that direction, and then the relative lengths of the arrows will indicate the relative sizes. So an arrow that would represent this location would be that, pointing in the negative direction, and the arrow represents a distance of 2 meters. Let's say whatever it is that's traveling, somebody in a car or somebody just walking down the street, starts at this location and ends up at that for the final location, plus 3 meters. Again, there are 2 pieces of information here. Location is a vector which contains 2 pieces of information, a direction and a size. 3 is the size. That means you have to travel 3 meters to get to this point if you're starting from the origin. And the direction indicated by a plus sign means you have to travel in the positive direction if you're starting at the origin and want to get to this point. And this also, being a vector, can be represented by an arrow. The magnitude of this location vector is 50% larger than the magnitude of this. So the arrow would have to be 50% longer to indicate that it's larger, and it would have to point in the positive direction. So there's an arrow that represents the final location. And this arrow represented the initial location. Okay, one more thing about the notation that I use. Well, many quantities that we deal with are vectors. A thing that has both a direction to it and a magnitude or a size. Magnitude is just a synonym for size. To make it clear that I'm talking about a vector, something with those 2 pieces of information, I'll put a little arrow over top of the algebraic symbol. So all of these locations, x final, x initial, are referring to vectors, So I draw an arrow over top to remind myself, to remind you, that we are talking about vectors. We're talking about a thing that has direction information that has to be taken into account, as well as just size information. Right? The size means that this point is 3 meters away from the origin, and then the sign tells you which way you have to go when traveling 3 meters in order to get to that location, if you start at the origin. Okay, that's just a way of talking quantitatively about location. But since we're talking about motion, we are talking about change in location, and that's what we'll get into in the next video.